Hey, Honors Pre-Calc. Today we're going to be learning lesson 8.4, one-sided limits. The essential question today is, how can one-sided limits be used to determine the value or existence of any limit? Here's what we're going to do. Students will know how to evaluate one-sided limits. There can be a left side limit or a right side limit. You will know why one-sided limits are helpful in evaluating the two-sided limit of a function at a point. And you'll understand a new definition of a limit that includes one-sided limits. You should already know what a limit is from the past going into this lesson. And here's an example of something you'll be able to do. Find the limit as x approaches 0 from the left and as x approaches 0 from the right for this function, the absolute value of 2x over x. All right, so let's get into it. All right, 8.4, one-sided limits. First of all, even if a limit fails to exist because a function approaches different values from the left and from the right, a one-sided limit can exist. So if we are approaching a limit from the left, this is the notation that we want. You'll have a function plugged in here for f of x. L is the answer. C is the value that we're approaching. And this little tiny minus sign, that's kind of where an exponent would be over the C. That means we're approaching from the left. If it's a plus side instead, it's because we're approaching from the right. And how you can think about that is if we are looking at a graph with an x and a y axis, let's say the C that we are trying to approach is right there. It could be anywhere, but it's an x value. So if we're trying to approach it from the left, think about it as if we're coming in from the negative end of the x-axis. So it's coming from negative infinity to the point. So that's why there's a negative. If we're coming from the right, it's coming from positive infinity. So that's why we have a plus sign there. So this would be coming from the left. This would be coming from the right. Okay, so that's how you can kind of keep track of that. And so what we're going to be doing, especially as we get onto the back of the page, is using this new limit definition. If f is a function and c and L are real numbers, then the limit as x approaches c of f of x equals L if and only if both the left and right side limits exist and are equal to L. So basically what that means is if we have a left side limit and a right side limit, and both of those limits are the same, then the overall limit exists, and it is that same value. If the left side limit and the right side limit are not the same, then the overall limit isn't going to exist because it's approaching two different values, right? That's part of something that we've learned before. But let's take a look at example 1. Find the limit as x approaches 0 from the left and as x approaches 0 from the right for f of x equals absolute value of 2x over x. So what I'm going to do here is just kind of sketch the graph, and you could use your calculator or Desmos to take a look at this. Basically what's happening here is if we plug in any positive x value, the answer is going to be 2. And if we plug in any negative x value, it's going to be an absolute value on top and negative on the bottom. So it's going to end up as negative 2. So the graph looks like this. If we wanted to make a table, all of the values below 0 for x would have a y value of negative 2. And all the values above 0 would have a y value of 2. But I think we can just use this graph to answer this question. So we're going to have two answers. The limit as x approaches 0 from the left, that's what that little negative means, of f of x. Since f of x is defined up here, I can just write f of x in the limit statement. And so as we're approaching 0 from the left, the y value, even though it doesn't exist when x is 0, the y value is approaching negative 2. The limit as x approaches 0 from the right, little plus sign, means we're looking from the right as x approaches 0, and all of the values are 2 all the way leading up to x equals 0. So the answer is going to be positive 2. That's the same thing we're going to do for letter B. Let's take a look at the graph this time. We have the limit as x approaches 6 from the left and as x approaches 6 from the right. So 1, 2, 3, 4, 5, 6. And this time, any values greater than 6 cause a y value of 1. and any values less than 6 cause a y value of -1. Like that. Okay? Now, the graphs aren't always going to be absolute value. They're not always going to be just straight lines that disconnect. We will see some piecewise functions on the back, but that's just what these two examples happen to be. But let's answer this question. So as x approaches 6 from the left, and as x approaches 6 from the right, don't forget we need to actually write the function in here. You can't just say lim equals. That's like leaving off part of the statement. It's a limit as x approaches 6 from the left of f of x. All of these things are required. So from the left, we're approaching a y value of -1. From the right, we're approaching about y value of 1. Hopefully that makes sense. And we're going to move to the back. So on the back, we're going to use the limit definition that we have now to actually find the limit as x approaches 1. So what we're going to do is we're going to find the limit as x approaches 1 from the left and the limit as x approaches 1 from the right, compare them and see if they are the same. So the limit as x approaches 1 from the left of f of x. This is a piecewise function. It might have been a little while since we've seen these, although they might have been earlier in the unit. But what it means, if you forget, is for any x values that are less than 1, this is going to be the graph, 4 minus x. Whenever x is greater than or equal to 1, we only use this expression for the graph, 4x minus x squared. So when x is approaching 1 from the left, it means we are looking at x values less than 1. All we have to do is find that part of the piecewise and use direct substitution. So we can do 4 minus 1 because we're plugging in 1 and we get 3. Now, even though plugging in 1 into f of x would result in us using the bottom expression because that's when we are equal to 1. If we're approaching 1 from the left, it's in the top function because that's where x is less than 1. Then we're going to plug in 1 from the right, and that means we're going to be using the bottom function because that's when x is greater than or equal to 1. And so we have 4 times 1 minus 1 squared, and we end up with 3. And what do you know? Both the left side and the right side limits equal 3. Therefore, the overall limit as x approaches 1 equals 3. In case you haven't seen this, I believe we used this earlier this year, but 3 dots in a triangle like this is a very mathy way of saying therefore. And you can use it at the end if you kind of written out an algebraic explanation for why something is true, then you can write therefore this. So since the left and the right side limits are both 3, therefore the overall limit equals 3. Okay, let's try one more question. Letter B, the limit as x approaches 2 of g of x. Just like with the first one, we have 2 different expressions within our piecewise function. One is for x is less than or equal to 2. One is for x is greater than 2. And since both of these are continuous lines, really, then we won't have any issues just using direct substitution. So the limit as x approaches 2 from the left is going to use the top one. So we have 2 minus 1 and we get 1. The limit as x approaches 2 from the right is going to use the bottom one because that's when x is greater than 2. So we have 2 times 2 minus 3, or 4 minus 3, which is 1 again. So since the left side limit and the right side limit were both equal to 1, therefore the overall limit as x approaches 2 of g of x equals 1. So there you go. That's how that works. And that is that. So if you have any questions when you're doing the worksheet, don't hesitate to reach out. Thanks for watching. Have a great day.